Okay, so how far did we go in the last class? Invariant subspaces, these are something that we did. How far did we go? Can you tell me the last problem which we did? Third one, no?
এই এক্সারসাইজটা নয়, আগের এক্সারসাইজটা।
Number 4 I think we did. Number 5 we did.
এটা
Yeah. I can remember doing this. And this also I think. Diagonalizable operator.
হ্যাঁ হ্যাঁ হ্যাঁ।
Prove that if E is a projection on R along N, then I minus E is a projection on N along R. Okay, so E is a projection V to V such that range E is R and kernel E is N, right? But if you remember, V was R direct sum N, right? Right? So, and any V was written to be EV plus V minus EV, right? This part was in N and this part was in R. But what is this? What is this? V minus E of V is nothing but I minus E of V. True? So, N, that is kernel E, is nothing but range I minus E. True? Okay. So if you square I minus E, what do you get? I minus twice E plus E square. That is I minus twice E plus E, that is I minus E. So I minus E is also a projection, right? So I minus E is a projection. Call it, say, star. Replace E by I minus E in star. What do you get? Kernel, because this is true for any projection, na? Kernel I minus E is range I minus E, right? That is range, okay, which is R. So we have obtained the result, huh? What they were doing, what they were asking for. 8. So suppose you want to EK linear operators on the space linear operators on the space V V such that summation ei is I. Prove that if eij is 0, then ei square ei is I for each I. In the case of 2, prove that if e1 is I, then e1 is 0. Okay. So it is given that summation ei is I. Okay. Prove that ei ej is 0 for I. If this, then ei square is. So part A is pretty easy, na? e1 plus ek. Suppose you get I. So suppose you product this by ei. Okay. So what do you get? ei e1 ei ek is ei, right? Now which of the terms in the left hand side will survive? Which terms in the left hand side will survive? Only I equal to I term, isn't it? Because of this criteria, we get ei square is equal to ei, isn't it? Because if ei and ej, the product is 0 if I am not equal to j. In the case k equals to 2, prove that the converse of a, that is if e1 plus e2 is I, so k equals to 2. Prove the converse of it, that is if e1 plus e2 is I and e1 square is e1, e2 square is e2, then e1 and e2 is 0. Okay, let's see. Suppose e1 plus e2 is I. Let's square it. I, that if e1 square is e1 and e2 square is e2, so this is e1 and e1 e2 plus e2 e1 plus this is e2. e1 plus e2 is I, huh? No. Why I am doing this way? Sorry. Product this by e1. You get e1 square plus e1 e2 equals to I, right? e1 square is e1 plus this is e1 e2. Okay, that is e1. Yeah, just cancel it out. So e1 e2 is 0. Okay. Similarly, e2 e1 is 0. So the next. V is a real vector space and E an idempotent linear operator on V. Okay. That is a projection. Prove that I plus E is invertible. Find I plus E inverse. Okay, let's do it. Okay, so if you remember, E is a projection operator, right? So E square is E, This implies E satisfies the polynomial x into x minus 1. Is everyone present in the class? No, not I think.
I mean, most of them are missing the class. What the hell is happening? So I mean, there are a ton of people. Rahul is here. Devargo is here. Tiasha joined the class. Yeah, Tiasha is here. Pritam, where is Pritam? Pritam is not in the class. Pritam is not in the class. Raghi was, yeah, Raghi is still there. Pritam is not in the class. Piyash is not in the class. Vibhushan is here. Yeah, Vibhushan is here. Shubrita is here. Then Omnidipto is here. But Sayon is not here. Then Nikhil is not here. There are almost 8 people not present in the class.
How can this go on? Okay. It satisfies the polynomial x minus 1. So the minimal polynomial of E is x or x minus 1 or x into x minus. So minimal polynomial of E splits into distinct linear factors. This implies E is diagonalizable.
Okay.
So another thing you can observe. Yeah, another thing you can observe. So V is R direct sum n, right? We have seen that where R is range G, n is kernel E. So suppose alpha 1 to alpha k be a basis of R and alpha k plus 1 to alpha n a basis of n. That is alpha I equals to E beta I for some beta I in V for I from 1 to k. This implies E alpha I is E square beta I, that is E beta I, that is alpha I. Okay, and E alpha I is 0 if I k plus 1 to n. Okay, we are creating an explicit basis for it. Okay, since E alpha I is alpha I for I running from 1 to k, alpha 1 to alpha k are CH vectors of E with respect to CH value 1, and alpha k plus 1 to alpha n are CH vectors of E with respect to CH value 0. So if beta is this alpha 1 to alpha n, then what is E matrix of E with respect to beta? 1 1 1 in the first k places, 0 0 0, right? That is I k and 0 everywhere else, right? So what is I I should write in, that is I v to v. Okay, the matrix. So what should be I in E in this basis? See, I in every basis is I, na?
The identity matrix is the identity matrix is identity in every basis. Because P inverse IP is always I. So what is it? This is beta plus E beta, that is In plus IK 0 0 0. What do you get? You get 2 in first k places, then 0, then 1 1 1 1, right? So you get 2 IK and In minus k. It is invertible, na? This is invertible, na? Which is invertible? So, and what is I plus In plus E inverse? This is a diagonal matrix, right? So you can rightly just do it like this will be half In minus k 0 0 In minus k. Okay. Okay. Now 10.
With every passing moment, I am just thinking this might, the machine might get switched off
Any given point of time. You are 15, right? So let's save whatever. What a fail. Okay. You guys read 10 for 2 minutes. Try it. Let me think as well. Just give me 2 minutes. Try. E is a subfield of complex number. Field of characteristic 0. E is a finite dimensional vector space over A. Suppose E1 to E are projections on E. This is right. Prove that Ti is a 0 for R. Okay. Hello. Okay, so let's see. Number 10. It's 6.6. Okay. Okay. So let's first copy number 10. So if the field is characteristic 0, we find a dimensional vector space. Summation ei is I and ei square is ei. We have to prove ei is 0. Okay. Okay.
So E1, to EK, you multiply it by EI. EI. Okay.
So ei square is ei, right? So we can write it this way, that ei ej summation j not equal to I plus ei square is equal to ei. Cancel them out because ei square is ei. No, wait a minute. They haven't mentioned that ei square is ei, na? Wait a minute. What happened? Oh, projections. It is given that they are projections. Yeah. So, given that ei ej j not equal to I is 0, you take the fresh function, fresh summation ei ej j not equal to I is 0. So, take the sum outside. Since this is a linear function,
Summation trace EI j not equal to I 0. Okay, now observe one thing. EI
ei ej have eigenvalues. Trace ei is less than equals to 0, greater than equals to 0, right? Because what is trace ei? If you write down ei in that basis as before, like the one basis that we used for the last problem, I think. Yeah, for this basis, if you write down, then you get what? A matrix of this. And observe that the number of eigenvalue 1 occurs how many times? The rank of E, right? So trace of, this is trace of this is nothing but rank of EI, na? So trace of EI is also greater than equals to 0. Thus, you get EIEJ. This sum is 0 with each of them being positive. So, EIEJ is 0. Okay. There is an alternative method as well. You can take this method. You can take this method as well. Like, let Wi be the range of EI. Now we claim that V is direct sum Wi I running from 1 to k. Now, as I is summation EI 1 to k, this implies that V is summation Wi, right? We will have to show that this is direct sum. But the span is clear, no? We show that dimension Wi is trace EI. But that is clear, no? We just show. We have shown that trace EI is rank EI. That is nothing but dimension range EI, and range EI is dimension Wi, right? So this is true. Each EI is diagonalizable. So there exists beta I, a basis of V such that EI restricted to beta I 1 1 1 1 of this form, right? Where a number of 1 is, we know, rank EI times. Okay. Now,
I is summation EI. Okay. I restricted to beta. This is nothing but the identity matrix of the order n. That is sum EI restricted to.
but I need, can I really do this beta I part? No. Let's do this. Okay, so E1 to EK is I, right? Okay, so take trace. Now trace I running from 1 to k is n. This implies, as we have seen, trace is dimension wi na, is n, right? Right. So this implies v is direct sum. Understood? Clear? This is. See, we have already shown this line. We have already shown that v is inside this. So the summation, so the dimension of the summation should be greater than equal to v. Because of equality, there is no overlap. Because if there is an overlap, we have to subtract that dimension. Na? Okay. Now 11. You remember what V1 not was? Do you remember? S was a subset of V and S naught was defined to be F belongs to V star such that F of alpha is 0 for all alpha belongs to S, annihilator of S. Remember? And there was, if beta is the basis of beta V, then there was a dual basis beta star of V star. You remember these things, na? That if this is alpha 1 to alpha n, this was f1 to fn, and the dual basis means fi alpha j is Kronecker delta. Okay? And there was a bijection, I mean from this, from alpha I to vi, fi. This was an isomorphism. Okay? These are some things that we have proved in the third chapter.
Okay. So V be a vector space, W1 to Wk be subspaces of V, and let Vj is where the jth summand is absent. Suppose that V is W1 to direct sum Wk. Prove that the dual space V star has the direct sum decomposition this. Okay. Let's see. Clear? The problem is clear?
Okay. So, to solve the problem, you send EI V to V by this. So EI is our projection such that projection onto the EI square is EI and range EI is WI. Okay. So onto W1. So of course some obvious things you get immediately is summation EI is I running from 1 to K, and EI is 0 if I not equal to J. These are some immediate observations. So you define EI star V star to V star sending, you send F to F compose EI. Okay.
Now we claim that EI star is a projection of V star.
Okay.
So let's see. So we will have to show EI star square is EI, right? That is we have to show. Okay. So let F belongs to V star. So you apply EI star of EI's.
দাদা EI হবে নাকি EI স্টার হবে?
দাঁড়া ভুল করে। You apply this on F. Okay.
But we have done this, right? That A star compose T star, this is nothing but S compose T whole star, isn't it?
I mean, what is this?
A star compose T star of F, suppose. What is that? F of A star compose T star, no? So that is A star of T star F compose T. Okay, just act it on a V, any V. What do you get? EI star of F compose EI of V, right? You break this way. That is F compose EI of EIV, right? Which is F compose EI square of V, which is F compose EI of V. That is EI star of F of V. Okay. So EI star
Square is EI star. Okay. So this is the projection.
Now, this was claim 1. Now we may claim 2. Summation EI star 1 to K is I. Okay. This is our, I of V star. Okay. So again, let
F belongs to V star. Summation EI star of F of V for V belongs to capital V, for V belongs to capital V. This is what? Summation I running from 1 to K EI star of F of V that is summation identity from 1 to k if compose ei of v. If is a linear functional, take if out. Summation ei is I, remember? So this is f of v. Summation ei star I. Okay. Now claim 3. Range ei star is vi naught, that was w1 to w I minus 1 plus wi plus 1 to wk. Okay, so we will have to show this. Okay, so let G belongs to range ei star. Okay, it means there exists f belongs to such that ei star of f is G, which means if compose ei is G, so let alpha I belongs to vi. Okay, we will show that G kills this alpha I. Okay, so G of alpha I is if compose ei of alpha I but ei alpha I should be 0, na? You see, because range of ei is wi, right? Range of ei is wi, na?
And alpha I was taken from, just a minute, what happened? Just a minute. Why is ei alpha is 0? Okay. Because of this. V is the direct sum of this, na? V is the direct sum of this, na? So once you take alpha I from wi, so this alpha is not in any of the wi's, right? If ei alpha I is 0 as range ei is wi and v is direct sum wi, so alpha I is not inside wi, I mean not inside what? Not inside vi, I should write. Yeah. Thus what do we get? Not inside vi. Just a minute. So if belongs to vi not? No. And alpha I belongs to vi. So alpha I belongs to vi, na? This implies alpha I is not in wi. That's the reason. I mean, it is in
in the other copies, if you remember. I should write this. I mean, not only doesn't belong to Wi, you understand? I mean, what I am trying to say. Understand this. Alpha I belong to Vi, okay? And what was Vi? Vi was this, right? I think missing. Wait a minute. What did I write here?
EI star is VI naught.
This doesn't make sense. Sorry. So this is what I am trying to prove. So alpha is in Vi. So understand, alpha is in the other copies, right? Not in this copy. Right this way. Best option. Okay. So this is 0. So this implies G belongs to Vi naught, because for any alpha I belongs to Vi, this is true.
Again, if belongs to Vi naught, so let V belongs to capital V, then f of V is f of Wi plus f of Vi, where Vi belongs to Vi and Wi belongs to Wi. You remember what Vi is? Yeah, this is Vi. This is Vi. Okay. So Vi, f belongs to Vi naught, so it will kill this part. So fv is f of Wi. Now, what is Wi, by the way? What is Wi? But Wi is EI of V, right? Right, na? Range of EI. If you apply Vi is Vi plus Wi, if you apply E on V, you get Wi. So f of V is if compose EI of V, that is EI star f is f, which means f is in the range.
Okay. So we have established this claim that range EI star is Vi naught. Okay. So thus now we know that V star has this decomposition range EI star. Hence this decomposition of Vi naught. Okay. Okay. So let's move on to invariant direct sum. We primarily are interested in direct sum decomposition of V. Subspace is invariant and some given linear transformation. Okay. We want to break V into a direct sum where each subspace of the decomposition is invariant under some T. Given such a decomposition, T induces a linear operator Ti on each Wi by restriction. The action of T is then this way. Yeah, of course.
They are actually generalizing the idea of the product. Okay, if you can understand. See, if I is summation ei, where each ei is a projection, then we have seen that this is nothing but summation eiv, na? Okay, but we also know if we let eiv is alpha I, then what is ei of eiv? That is ei of alpha I. What is that? Ei of eiv is eiv, na? So alpha I is ei of alpha I, right? So we can write V as, I mean, what I am trying to say is that ei of V is alpha I, which is E of alpha I, right? Understood? Here you see, ei of V is ei of alpha I. But ei of alpha is alpha I, na, again? I am trying to say this. I am trying to say this. So, V is summation eiv. Okay. Now write alpha I as eiv. Okay. Now take what do you get? Ei alpha I. What is that? That is ei square V. Ei square is ei, that is eiv, which is alpha I. So, they will, so we can write V as I of V as ei summation ei alpha I, right? So they are trying to generalize the idea of T actually. So now you get, obviously you multiply this by T, okay, get TV, immediately you get summation T eiv, ei alpha I. So that's your breakup. They are trying to generalize this idea. Okay, I would request you to just go through this briefly before theorem 10. All of you have the PDF, na? All of you have the PDF. So just go through this part before theorem 10, please. You have 3 to 4 minutes. Just go through it. So let's see theorem 10. Let T be a linear operator on the space V, and let W1 to Wk and E1 to Bk as in theorem 9. So what was in theorem 9? So V is the direction of decomposition, Ei is the projection, Wi is the range of Ei, I is summation Ei, this Ei is 0 and this is this. Okay. So under this setup, then a necessary and sufficient condition for each subspace Wi to be invariant under T is that T commute with each projection Ei, that is this. Okay. So they say that this is the necessary and sufficient condition.
Let's see. Suppose T commutes with each Ei. Let alpha belongs to Wj. Then T alpha is Tej alpha. Then Ej alpha is alpha. Okay. Because alpha is in Wj, na? So Ej alpha is in alpha. So T alpha is this, commutes with this. So Ej T alpha. So T alpha is in Wj, range of Ej. So one part is done. Assume now Wi is invariant under T. We shall show that Tej is Ej. Okay. Let alpha be any vector in T. Then alpha has this breakup. You multiply it with T. Apply T. So you get this. Since Ei alpha is in Wi, which is invariant under T, we must have T Ei alpha is Ei beta I for some vector beta I, that is they say T Ei alpha, see Ei alpha is in Wi and Wi is T invariant, right? So T Ei alpha is also in Wi, which is range Ei. So there exists beta I such that T alpha Ei alpha is alpha Ei beta I. Okay. Then apply Ej on T Ei alpha. Ej on T Ei alpha. What is that? That is Ej Ei beta I true. Now this is 0 if I not equal to j, and Ej Ei is Ej, of course, that is Ej square is Ej if I equal to j. Okay. So Ej T alpha. Now they are doing this. First they are doing T alpha, this line. Yeah, they are applying Ej on this line. Okay. Now Ej T E1 alpha. This is Ej beta j, right? Because of this line. Because of this, Ej T Ei alpha is nothing but Ej beta j. Okay. That is Tej alpha. Okay. Now you see Ej T is Tej for any alpha. Okay. So it is commuting. Now they are willing to describe a diagonalizable linear operator T in the language of invariant direction of decomposition projections which commute with T. Okay. This will be a great help to us in understanding some deeper decomposition theorems later. Okay. The reader may feel that the description which we are about to give is rather complicated in comparison to the matrix formulation or the simple statement of characteristic values. Okay, so basically they are trying to characterize a diagonalizable linear operator in terms of invariant direction decompositions. Let's see what they are doing.
So they are saying that T be a linear operator on a finite dimensional vector space V.
If T is diagonalizable and if C1 to Ck be eigen distinct characteristic values, then there exist linear operators E1 to Ek such that T is this C1 E1 up to Ck Ek, I is this, Eij is 0, Ei square is Ei. Okay. And range of Ei is the characteristic space for T associated with Ci. Okay. Conversely, if there exist k distinct scalars C1 to Ck and k non-zero linear operator E1 to Ek which satisfy these conditions 1, 2, 3, then T is diagonalizable and C1 to Ck are distinct characteristic values of T. And condition 4 or 5 are also satisfied. Okay, let's see. Suppose T is diagonalizable with distinct characteristic values this. Okay. Let Wi be the space of characteristic values associated with Ci. That is, Wi is all those vectors V belongs to V such that PV is Ci. Okay. We denote it by WCI sometimes. Okay. Since T is diagonalizable, there is an eigenbasis, so V is this. Okay. Let E1 to Ek be the projection associated with the decomposition. That is, Wi is range Ei. Okay. Associated with this decomposition.
Projection onto the ith coordinate. Ith summand. Then 2, 3, 4 and 5 are also satisfied. We know that. To verify 1, with this we know that this is satisfied, right? These are satisfied. We know that from theorem 9. They have to satisfy 1. Okay, let's see. To satisfy 1, proceed as follows. Take alpha in V, then alpha has this decomposition. This T alpha, Te1 alpha. Now E1 alpha is in W1, which is the characteristic space corresponding to C1. So this is nothing but C1 alpha, C1 E1 alpha. Because of this definition, okay. Every vector in Wi is a characteristic value with respect to Ci. So you have this. Now suppose given a linear transformation T along with distinct scalars and non-zero operator Ci which satisfy 1, 2 and 3. Let's have a look at 1, 2 and 3 again. So T is a linear operator which satisfy, and there are k distinct distinct scalars and k projections such that you have this. Okay. 1, 2 and 3. Let's see what they are doing. Both sides of I and obtained immediately. Since Ei Ej is 0 and I not equal to j, we multiply both sides of I by Ei and obtain immediately that Ei square is I. Okay. Multiply T, suppose this equation CkEk, multiply this by Ei. Okay, let's see. Suppose Eit is then what do we have? C1 Ei E1 plus Ci Ei square up to Ck Ei Ek. Okay. But Ei is 0. So every one of them is 0. Only Ci Ei square is left. Okay. Only Ci Ei square is left. So Eit is Ci Ei square. This proves that there is a non-zero vector in the null space of T minus Ci I. Wait a minute. How do they get that? So EI T. Oh, sorry. I should have done this right. Extremely sorry. I mean, multiply by right side. Do this TEI. That then you get CIEI square also by the same logic. Then you get T minus CIEI of EI is 0, right? Choose a vector outside of kernel EI. Choose a vector outside of kernel EI. So EIV is non-zero. So T minus CIEI of EIV is 0. That is EIV is an eigenvector with respect to CI. Am I right? No, not exactly. Sorry, what happened? Oh, CIEI square is CIEI, na? CIEI, sorry. Now it is. So T minus CII of EI. Now do the same thing. V doesn't belong to kernel EI. So EIV is non-zero. So you get T EIV is CI EIV. So EIV is CI is a characteristic value. Okay. Yeah, which shows that any vector, assumed any vector in the null space of this, since which shows that any vector in the range of EI is in the null space of this, true. Since we have assumed EI not equal to 0, this proves that there is a non-zero vector in the null space. Yeah, so CI is a characteristic value. Furthermore, if CI are all of characteristic values, furthermore T cannot have any other characteristic value, because if C is any scalar, then T minus Ci is, what was T? T was C1 E1 plus CK EK, right? From that you obtain this. So if T minus Ci alpha is 0, we have Ci minus C alpha I is 0 for all I, because this is a direct sum decomposition. If alpha is not the 0 vector, then EI alpha is non-zero for some I. So we have Ci minus C is 0, right? If alpha is not a 0 vector, then there is some non-zero projection, na? Then EI alpha cannot be 0. If EI alpha is 0 for every I, then alpha is a 0 vector. Because if alpha is this, na, E1 alpha plus this. So if alpha is non-zero, there is some I for which EI alpha is non-zero. So Ci is C for some I. Certainly, T is diagonalizable, since we have shown that every non-zero vector in the range of Ci is a characteristic vector of T, and the fact that I is this shows the characteristic vector span V. Okay, we are done. All that is remains to be shown that null space of T minus Ci is exactly the range of Ti. But this is clear because T alpha is Ci alpha. Then summation deriving from Ca Ci alpha is 0. For each j, okay, Ej alpha is 0. Okay. So that concludes the theorem. Okay. So that concludes the theorem. If T alpha is this, then wait a minute.
where does this suddenly come from? Oh, T was C1 E1 up to CK EK. So T alpha is this, and alpha is EI alpha summation. So T minus CI. They write. Okay, I understand. So T alpha is CI alpha. They are writing it as summation CI EI alpha equals to, EJ alpha equals to CI summation EJ alpha. That's it. So you take this out, EJ alpha. Now since this is 0 and these are in these are in, where is this thing? Where is this term? This summand? These are in WJ, which forms the direct sum decomposition. So they are independently 0. So EJ alpha is 0 because Ci not equal to Cj if j not equal to I. So EJ alpha is 0 if j not equal to I. Since alpha is this and EJ alpha is 0, it implies that we have alpha is and equals to EI alpha. Yeah. This proves that alpha is in the range of EI. Okay, so this is done. See, we will resume from this, okay, on the next class. Shubhrita, remind me that we will start from this Lagrange's polynomial, okay. This is very important. We will start from this, after this, okay. We will start after this, because Lagrange's polynomial is very, very important. We will start from page 617, 217. Shubhrita, Tiyasha, please remind me. Okay, let's conclude today.